Welcome to a lesson in proportional reasoning. Suppose you are creating a clay at home for an art project. The recipe you have calls for 2 cups of water and 4 cups of flour. You would like to make more clay than the recipe calls for, so you decide to put 6 cups of water in the bowl instead. How many cups of flour should you use? So the very first part of this situation we should look at is what are the quantities in this situation. So remember that a quantity is an attribute of an object or a situation that we can imagine measuring. So looking at this situation, we're going to make a table of values. And so let's take a look at the quantities. The first thing that we can notice is that there are cups of water that we're measuring. And the other part that we can measure in this situation is the cups of flour. So that's how we're going to create the table. We also can imagine that as the number of cups of water is increasing, so will the cups of flour in order to maintain the correct mixture. So the quantities in the situation are changing together. Another way to say this is that the quantities are covariant. So let's take a look. First of all, there's 2 cups of water. And when you have 2 cups of water, that's associated with 4 cups of flour. That's what produces the correct mixture. But we want to make more clay, so what we also want to do is to figure out, okay, with 6 cups of water, how many cups of flour should you use? So we'll assign a variable, we'll call it f, and that we're going to use to identify the unknown amount of cups of flour. So what we're going to do is we're going to engage in some proportional reasoning. And there are a couple of ways to do it. There's really 3 ways to do this. So that's what we're going to be looking at. So if 2 quantities are proportional, there's 3 ways to think about how these quantities are in proportion to each other. One way is to think about scaling. So if you scale one quantity by some factor, then you must scale the other quantity by the same factor. Another way to do this is to think about a constant multiple. So when one quantity is always some number times as large as the other. And lastly, another way to think of proportionality is to notice that the ratio of 2 quantities is always constant. And so this is a constant ratio perspective of proportionality. What we're going to do is look at all 3 ways to think about this. It will produce the same answer, but there are different ways to think about it, and oftentimes, depending on the situation, sometimes thinking about it via scaling is easier, sometimes thinking about a constant multiple is easier, and sometimes thinking of it from a constant ratio perspective is easier. So the situation will help you decide which of those 3 ways of thinking proportionally is the best for that situation. So let's go. The first thing we're going to look at is the scaling perspective. So when you scale one quantity by some factor, you must scale the other quantity by the same factor. So how does this work? So we're going to compare 2 to 6. What do we need to scale 2 by to get to 6? So to do that, we would multiply 2 by 3. In order for the quantities to stay in proportion, that means that you would need to scale 4 by that same number, which is 3. So to figure it out, you take 4 times 3. That tells you that f is 12. That tells you that the cups of flour is 12. That would what would keep the mixture in proportion. Now let's look at the constant multiple perspective. What it is we're going to relate the cups of water to the cups of flour, because what we're doing is one quantity is always some number times as large as the other. So you're comparing across quantities. So let's see. 2 times what is 4? 2 times 2 is 4. So that is going to be the constant multiple in the situation as we compare water to flour. So let's see, 6, what we're going to do is multiply that by 2. That's that constant multiple. So 6 times 2, that tells us is 12. So that tells us that the cups of flour is 12. Notice that the answer is the same as before when we were doing scaling, but it's a different approach to come to that same conclusion, that you need 12 cups of flour for 6 cups of water to keep the quantities in proportion. Now let's look at the last one, which is the constant ratio perspective. So it says that the ratio of 2 quantities is always constant. What that tells us that the cups of water to the cups of flour will always be in a constant ratio. So let's take a look at the one that we do know, which is the 4 cups of flour to the 2 cups of water. According to that, this is always going to, since that's the same, that means that 4 over 2 is going to be the same as f over 6. Now I'm not going to solve the algebraic equation using cross multiplication, although you could. we're going to look at it really looking at it from that constant ratio perspective. So according to this, 4 over 2 is 2. That would tell us that f over 6 should also be that same constant ratio, which is 2. So using related facts, we know that if something divided by 6 is 2, that means that 2 times 6 must be what is the unknown. So it follows that f is 12. So 12 divided by 6 is 2, and that again comes to the same conclusion as before, but from a constant ratio perspective. So let's look at some other ones. What I've done is I've added a few extra numbers to the table, and what we're going to do is use this ways of thinking about proportionality to see whether the new values, this new cups of water to cups of flour, are in a proportional relationship to the original mixture. So we're going to use these different ways to reason proportionally to determine whether the following mixtures produce an equivalent clay mixture as the original recipe. And again, we're going to investigate scaling, the constant multiple, and the constant ratio perspectives. So let's first focus on the scaling perspective. So what we do is we're going to compare 2 to 5. I'm going to say 2 times what is 5? Well, that number you need to multiply 2 by, is 2.5. So 2 times 2.5 is 5. So according to this, from the scaling perspective, when you scale one quantity by some factor, you must scale the other quantity by same factor. One of the things you'll notice that with scaling is that you're going down vertically. So you're comparing water to water and then flour to flour. So let's see. According to this, since we scaled the cups of water by 2.5 to get to 5 cups of water, we're going to need to do the same with the 4 cups of flour. So 4 times 2.5 is what? Well, when you multiply 4 times 2.5, you get 10. Notice that in the table you also have 10, which tells you that this checks off and that the quantities are in proportion. So 5 cups of water to 10 cups of flour is in proportion to the original mixture. Okay, let's look at the next group of values, which is the 1/2 cup of water and the 1 cup of flour. So we're going to again look at it. Now notice that each time you do scaling, the scale factor, the associated scale factor is going to be a different each time. So let's see, 2 times what is 1/2? So as you do this, you try to think 2 times what number is a half? That number is 1/4. 2 times 1/4 is a half. So that tells us that to go from 2 cups of water to 1/2 cup of water, we need to scale by 1/4. So for the quantities to stay in proportion, that means the corresponding value, the 4 cups of water, also needs to be multiplied by 1/4 for the mixture to stay in proportion. So 4 times 1/4 is what? So when you take 4 times 1/4, you get 1. Notice that is the same value that's also in the table, so that also checks. Now we're going to do it with the last value. So we're going to look at 2 times what is 4. So 2 times what is 4? That number is 2. So that tells us the scale factor for this relationship is going to be 2. So we're going to multiply 2 times 2 to get to 4. So that means that using the same scale factor, 4 times 2 is what? Well, according to that, 4 times 2 is 8. But notice that the number does not match with the number in the table. That tells us that the 4 cups of water to the 6 cups of flour is not in a proportional relationship to the original mixture. So that particular set of values, the 4 cups of water to the 6 cups of flour, is not in a proportional relationship because the number in the table should have been 8, not 6. Okay, now let's look at the constant multiple perspective. So the constant multiple perspective means you're comparing water to flour. So that's done horizontally across the table because you're comparing the input to the output. So let's see, 2 times what is 4? According to this, 2 times 2 is 4. That is the constant multiple. That would take you from the one input to the output. So what this tells us that when we're comparing all the other values, you should be multiplying by 2 to get from the cups of water to the cups of flour because one quantity is always some number times as large as the other. Again, this is from that constant multiple perspective. So 6 times 2 is 12. That matches, correct. And so what we're going to do is we're going to look at 5 times 2. Does that come out to be 10? Yes. Okay, does 1/2 times 2 equal 1? Yes. Does 4 times 2 equal 6? The answer is no. 4 times 2 is 8. But notice over here in the table you have 6. So the 4 and 6 is not in a proportional relationship to the original mixture. So again, with the constant multiple, notice that when we're going horizontally, that's the reason it is called a constant multiple, because it is always the same number that should relate the input quantity to the output quantity. Notice that the last set of values, 4 cups of water to 6 cups of flour, is not in a proportional relationship to the other values that you saw before. Okay, now let's investigate the last one, which is that constant ratio. So again, the cups of flour to the cups of water should be a constant in a constant relationship. So let's take a look. So looking at cups of flour to cups of water, 4 cups of flour divided by 2 cups of water, that's going to give us a rate of 2, or a ratio of 2. So that means that every other value should have that ratio, constant ratio of 2. So let's check that out. Does 12 over, okay, so when you take 12 divided by 6, that's 2. So that matches. Is 10 over 5 2? Yes. So that matches. Let's now look at 1 divided by 1/2. Well, that's a complex fraction, so we might consider rewriting this as an equivalent division statement, which means that's 1 divided by half. However, that means, so when you do 1 divided by half, you're trying to count how many copies of a half are in 1. There's exactly 2 of those. There's 2 1/2s in 1. So that is also in a constant ratio relationship. Let's look at the last one. 6 over 4. Well, 6 over 4 is actually 1.5. That is not the constant ratio of 2. Therefore, that last associated relationship, which is 4 cups of water to 6 cups of flour, that is not a constant ratio. That is not in proportion to the previous values. Let's also take a look at a plot of these values on a graph. So if two quantities covary, meaning that they're changing together so that they remain in a proportional relationship, a plot relating each input quantity to its corresponding output quantity would be on a straight line going through the origin. So looking at these values that are in the table, they've been plotted on a Cartesian plane where the cups of water is the input and the cups of flour is the output. The dot, which is 4, 6, was the one that was not in a proportional relationship, and it's highlighted in blue. So let's take a look and see if this claim is true. When you draw a straight line through the points, notice that it crosses through the origin, which is 0, 0, and they all line up. Also notice that 4, 6 is not on that line because it is not a part of that proportional relationship. So we're going to talk much more about this. The rule relating the input to the output is directly related to the constant multiple. If you recall from earlier, that constant multiple was 2. In this situation, to maintain the correct mixture, the number of cups of flour is always twice as large as the number of cups of water. In a future lesson, we're going to investigate this relationship more thoroughly, but this is an introduction to characteristics of proportional quantities and proportional reasoning. So more to come soon. I hope you found this helpful.